The first thing I want to talk about is our exam on Friday, and just to make sure everybody's got the procedures. I'll be here right at 8:30 on Friday morning at the start of a normal class. You don't have to come. But I'll be here for probably about a half hour. Zoom logs me out if nobody comes on for 40 minutes. So at 9:10 the meeting ends if nobody has any questions. But I'll be here just to answer any questions on Canvas. I'm going to share my screen with you. It looks like Canvas. Yep. If you go to your assignments tab, and you can see all the busy stuff you've been doing all semester. You got midterm one. It's currently not active, so you probably don't see it. But the first link will be the link to Mastering Physics. There's 15 questions in Mastering Physics. It should take you about a half hour to do those. And then also showing up under labs where midterm one is. Well, I just make this active real quick so that you can see it. All right, hopefully you're seeing it now, maybe. Yep. Okay, so you see that's a link to Mastering Physics. And I'm also going to have a Word, actually be a PDF document here. There'll be two problems that look like worksheet problems. Of course, you can download them. You don't have to print them out. You can just answer it on a plain sheet of paper, but then there'll be an assignment where you have to upload them, okay? And so both of these two things, the Mastering Physics assignment and the two problems that are like worksheet problems, will be available at 8:30 on Friday morning. You have all day to get them in. I decided the due date is 23, due time is on Friday at 23:59. As I was looking through it, I was kind of trying to figure out how long it should take you. Some people will be done easily in an hour. Other people, I'm thinking about 75 minutes is the max I would expect for anybody to work on the exam. Okay. The problems in mastering are worth 15 points, one each, and they're mostly short answer. Some of them you look at a graph and make a determination. They may have a numerical piece to them. You may need a calculator to answer them, but they should be fairly short calculations. The two problems that'll be on a PDF document, they are more like worksheet problems. In fact, some of them should look a whole lot like worksheet problems. One of them is a little longer. It's worth 15 points because it has multiple parts. And the second one is worth 10 points. It has multiple parts, but is just a little bit shorter. Okay. And resources that you can use for the exam. Just want to make sure we're clear on that. Anything that you find here in Canvas is fair game, right? Let me slide over to the modules tab. And,
Can I ask a question really quick?
sure, go ahead. Any questions this time? Go ahead.
For any chance it could be available before 8:30 because I have class all day and then I work that night.
Sure. What time would you want me to make it available at like 7? What time's good? I mean, I'll go earlier.
Yeah, like 7:30 would be perfect. Just so I have
Seven
a little.
o'clock it is. It's a
I have
deal.
a
I
question.
have no problem with that, but I won't be available. I'm not getting up early. I'm happy you do, but I'll be available for any questions anybody has. Once you open it up and you read it, you go, oh, what am I supposed to do? I'll be here at 8:30 still. But
Okay,
I'll
thank
open it up at 7. Not a problem. Anybody else? All right. So
Yes.
anything that's on Canvas here, and I think I mentioned right at some of you may have been logging off on Monday. I did make up an exam formula sheet, and that's just so that you don't have to go paging through your electronic textbook to get a formula you can't remember. And that will be on the PDF document of the exam. Okay. You can see each of these is a chapter. There's chapter 1 representing motion. There's all the worksheets at the bottom. My worksheet solutions are sitting there. Those might be handy for you, I hope. There's chapter 2, all the worksheets, the reading quizzes you did, my solutions to chapter 2 worksheets, the 3 of them that week. There's the first lab you did. I wouldn't discount thinking about what you did on labs. I hope to have lab 2 is, you turned it in last week. I hope to have it graded either today or tomorrow so that you should get some feedback on that. There's still a couple more from lab 1 that I have to grade. And of course, this week we're doing you're turning in lab 3, which is the inclined plane problem. That's always fair game. And then, of course, this week's lab is a projectile motion problem. Some of you will be working through it with Dr. Kem, and the rest will be working through it with me. And I think I told you I like projectile motion problems because they're very comprehensive on a lot of stuff we've done throughout the course of the semester, the first 5 weeks here. And so pay attention to the labs. Any event, don't discount the labs, I guess. There's chapter 3, all the worksheets, reading quizzes, my solutions. There's a free fall motion lab 2. And then I haven't yet posted, there were 2 worksheets from chapter 4. I'm still waiting. There are a couple people that haven't turned in. You only had to turn in the first one, but I'll post both the solutions to the week 4 worksheets at the bottom of this one, and that'll be done today. Okay. And of course, chapter 5, not on the exam per se, because it's applying Newton's laws. The problems are a little more complex, but that doesn't mean there won't be some questions dealing with Newton's laws. And so anything on Canvas is fair game for you for a resource. You'll see my notes are here. The PDF documents are my PowerPoint notes that I use. All fair game for you to use. Probably overkill. Any of the videos you want to go review if you need it for an exam, all fair game. Your textbook is fair game. Okay. Any notes you've taken, like your worksheets that you may have in a notebook or something like that, any notes while you were watching videos you made, those are all fair game. What's not fair game? Hunting the internet for solutions to problems. Okay, especially Chegg, of course. That's the big bugaboo that we just, I'm anti-Chegg. It has its place perhaps, but an exam is obviously not a time. And I only let you know that because, of course, last semester I had an issue on the final exam with students going to Chegg to find solutions. And that's one of the reasons why the time is somewhat limited, because I know Chegg has a problem answering service where you submit a problem and some expert responds to you. That generally takes more than a day, and that's why I can't give you multiple days to do the exam. Okay, sure, go ahead.
Okay, so if you're opening it at 7, can you leave it open till like midnight?
Because so it's still 7 to midnight. Yeah, it'll close. You got to have it uploaded by 23:59 on Friday night. Is that what you're asking?
Yes, thanks.
Okay, yeah, we're just extended 1 hour, 1.5 half hours earlier. That's no problem. I suspect only a handful of people that have special reasons, like they're working, for example, taking classes, would want that extra time. But I'm more than happy to make it earlier. But 23:59, right before 11:59 p.m. Sorry, I use military time a lot. That's when the exam's due, and I'll be grading it Saturday and Sunday. Okay. All right, so that's the exam. Any questions? What you can use, what you're not supposed to use? Obviously, you're on your honor. I'll have no idea if you're searching the internet for solutions. I'll have no idea if you're talking to somebody else, but obviously talking to somebody else, searching the internet for solutions, those are not authorized resources and do represent cheating. All right, stop sharing that. I do have a couple polling questions today, and I'm going to do some example problems as I often do. And so let me start sharing instead my PowerPoint notes. Last chance for questions on the exam. Not last chance, just email me if you got any questions. And of course, Friday morning, I'll be here once you open it up, if there's any issues. Oh, I think my intent is that if somehow you start the Mastering Physics section, those 15 questions, and maybe you only get 10 done and you got to go do something else, like go to another class and you want to come back, my intent is that you should be able to come back. I'll make sure that the settings allow that. But I've heard stories from students where Mastering wouldn't let them come back for a second attempt. But that my hope is that if you can only get through 10 and then you got to come back to do 5 later, that should be allowed. And I'll check that.
I have another question.
Yeah, go ahead.
So we can take, let's say I have time to take the Mastering exam in the morning.
Yep.
Can I do that and then take the other part after?
Absolutely. Yeah, they're completely independent. Yeah, as long as both are done by 11:59. Yeah, you can do the Mastering in the morning and then do the other 2 problems later in the day, in the evening or something. Just have them both in place by the end of the day, by 11:59. Okay. And again, the point breakdown.
I have another question.
Yep, go ahead.
I just want to make sure you said that we can use what's on Canvas.
Absolutely. Yeah.
To look back. So all of that stuff is going to stay on Canvas during the exam time.
What do you mean by that?
I've had professors that remove all the power.
No. Once I put something on Canvas, I'll be honest with you, I'm too lazy to take it down. Now, all the resources that are in Canvas, I consider those to be your notes. Those are your electronic notes, and I'm not going to take any down for the exam. It'll be there the whole period. And so if, for example, there's a problem and you go, there was a worksheet problem like that, it was close, and you open up that worksheet solution of mine, because it'll still be there, and you use that as a template, and you remember that, that's great. Okay. It's not, you're not going to find the exact same problems, obviously, but a similar problem might appear as one of the worksheet problems you've worked, or one of the lab problems you've worked, something like that. So everything will stay on Canvas. I won't be taking anything down. Okay.
Okay, thank you.
You bet. Good to go. Yeah, I'm not going to try to, my hope is that this is the first exam, right? We'll have another one, and then we'll have a final exam. And I think exams are learning experiences too. I fully expect, when I say a lot of people will be done in an hour, that's because you understand this material, you're doing well. Other people may have aha moments, learn some things on the exam, and that's okay too. If you have the afternoon to work the exam and you didn't know exactly how to do a problem, but you figure it out during the afternoon by using the resources that are on Canvas, you're mastering your textbook, any of your notes, that's an okay thing. All right, and so let's move on here. I know there's always angst on exam. I think most of you will do very well. I hope some of you took advantage of Max Tucker and Anna Hall last night in the drop-in for quantitative skills, because I'm not as much worried about the physics in many cases, because I think a lot of you understand the concepts, but I do notice when I'm grading things that some of your mathematical skills, getting components of vectors, adding vectors, Pythagoras' theorem, you're not practiced at those things. And so hopefully Max and Anna helped some people out. They both swore to me they would, and I'll know when I see Max in a couple hours here for class. All right, anyway, I'm going to share my PowerPoint screen, start a couple polls up, and then I'm going to do a couple example problems. Hopefully I'll finish them on time. We'll see how we say that, and I talk too long. So there you go, first one, and there's your question. And remember, the reading for today and the video, the pre-lecture video, had to deal with weight and apparent weight. And this question is looking at that. And I did the math for you. 50 kilograms times 9.8 meters per second squared, the acceleration due to gravity, which is how you calculate weight. That's the big equation for today, is 490 newtons. Interesting answers. I can almost see why you might think. All right, we got 26, 3 more people, and then I'll talk. All right, we're not waiting for whoever you are, the last person here. Ended it. All right, well, I'm going to share the results with you. And I think the 10 of you who picked D, you got it right, okay? Now, if you picked C, I'll let you know what you might be thinking that could be a correct answer there. The presumption here is when that cable breaks, the elevator is freely falling downward, okay? And when you're freely falling and you step on a scale, the normal force will read 0. And what we said in the reading last night in the pre-lecture video is apparent weight is the normal force that you would be having on a scale in this situation. Maybe a better question was one that was in the textbook. You're jumping off a trampoline, you leave the trampoline and you're going up in the air. And while you're going up in the air and then down, what's your apparent weight then? And if you put a scale underneath your feet while you're in that position, going up in the air or down, maybe off a diving board too, you're just falling freely, that scale would get no normal force and your apparent weight would be 0. Now, for those of you who said less than 490 newtons, you're on the right track. And maybe you were thinking the elevator would kind of have friction that wouldn't let it free fall, in which case there might be a small reading still on the scale. I can live with that answer for the 13 of you that pick C. But if it is free falling, truly, you have no apparent weight. Okay, and that's one of the things we believe about physics. In fact, one of the misnomers about space travel, and some movie producers get it right. I think the movie Gravity got this right, and we'll talk about this more in a couple weeks when we talk about gravity. But why are they weightless in the International Space Station? And the answer is a lot of people believe that, well, you're just so far from the Earth that the acceleration due to gravity gets smaller and smaller and goes to zero. And in fact, that's not why they're weightless at the International Space Station. The reason those people up there are weightless is because as you're in an orbit, you're actually free falling. And when you're free falling, you have no weight. So they don't go to the bottom of the International Space Station. They're free to float around the International Space Station. And if orbital motion and free fall are not something you see as a pair, come back in a couple of weeks. We'll definitely talk about that. We'll see how you are free falling, because the acceleration, the centripetal acceleration we talked about for an object going around in a circle, is exactly the acceleration due to gravity at that point in the distance from the Earth. And we'll calculate how G can change from 9.8 meters per second here at the surface of the Earth to some other value up at a location like the International Space Station. But they're actually in free fall motion up there, okay? And that's why they experience zero gravity, no apparent weight. All right, I'll stop sharing that. We'll go on to the next. Oh, and here's the words. There'd be no normal force, 0 newtons if you were to step on a scale, or were hanging from a scale, I guess, if it was one of those kind at the fish market that is a spring scale. All right, move on to the next one here. And launch poll. And this time, different G, right? You would expect, I hope, that the acceleration due to gravity on the surface of Mars would be different from on the surface of the Earth. And again, we'll talk about that in a couple of weeks. You'd be right. So this thing has been hurtling towards Mars, and now it's slowing down as it descends to the surface of Mars. What must be the free body diagram for this situation? So descending and slowing means the velocity is downward, but getting smaller, decelerating. $19, $21, we're getting there. $26, 3 more people. Okay, so I see 2, you have trouble with the polls, so I'm not going to wait. So it looks like 1 of you managed to get back in. Internet problems are always there. Thanks for letting me know. Just in your mind, get an answer. And here we'll end it, and I'll share the results. And I'm happy that most of the people have the right answer. B there, the 15 of you that picked B, you got it right. Here's the first question, I guess. This is the direction of the velocity, right? Going downward. But a second later, the velocity vector will be less. And then a second later, the velocity vector will be even less. And a second later, the velocity vector will be even less. And so this motion diagram here tells us that there is an acceleration that's upward, right? And that's the key. And of course, Newton's law says the net force, the sum of the forces, using that Greek sigma, has to be equal to the mass times the acceleration. Okay, and if the acceleration is upward, so does the net force. And so the question is, which of these 5 cases gives a net force that's upward? And I think that narrows you down to 2, that one and that one. This one would give you, A would give you a net force of 0. C and E would give you a net force that's downward. So they're clearly wrong. And why B is the better answer, I guess, is that you would identify the forces from our catalog. That must be thrust. And I always hate the fact that thrust and tensions both start with T. Okay, so maybe I should go force thrust from the engines of this thing. Okay, and then of course, this is the weight vector. And in order to be slowing, the thrust must be greater than the weight vector. So you have a net force, which is upward. So you have an acceleration, which is upward. So a downward velocity gets slower. Hopefully that makes sense. And I hope did the 15 people, but for the other, I guess, what about 14 that got it wrong, I hope that makes sense for you, because you'll see stuff like this on the exam. And that is, if you got this, you understand how to do Newton's second law problems. All right, I'm going to stop sharing. I'm going to stop sharing my screen. Any questions on what I did right there? All right, those are the two. We're talking about Newton's second law today. I want to go on to solve two problems for you. And I do that with my iPad here. All right, and hopefully I'll be able to screen mirror to, yes, look at that, technology working today. And I'll put that away. And you should be seeing the worksheet for today. And you know, I haven't commented on these, but I should. I've got these notes, A through B, A, B, C, D here, A through D. I didn't write them, so I probably should footnote where I got them from. A guy who was one of my mentors, I guess, to some degree at the Naval Academy, a guy named Dr. Paul Mikulski. He put these together. He was the course coordinator for the Physics 1 class there. If you recognize the name, yeah, he is related to the senator from Maryland, Barbara Mikulski. He's, I guess, her nephew, and he put these together. I think it's a pretty good list of things you should bear in mind when you're doing Newton's first and second law problems. Some things about how to create a good free body diagram that will be helpful to you, okay? How to select a good coordinate system, how to calculate the sum of the forces is equal to mass times acceleration, which without making a common mistake people often do with weight now, because we know that we've said as of today, you have to know how to calculate weight. Weight is equal to mg, and a lot of people just say, well, weight is equal to Newton's second law, ma. And you know, A is G, and then you get that misconception that the acceleration in the problem must be the acceleration due to gravity. Now, it's just a very coincidental thing in nature that we can find the weight by using the acceleration due to gravity and multiplying by the mass. It isn't simply F equals ma, where you just plug in G for A. It's an oddity of physics, a misconception. If you can work through it and get the problems right, I guess people can live with that misconception. But recognize Newton's second law doesn't just deal with one force. Newton's second law deals with the totality of all forces, added as vectors using the rules for vector addition and setting it equal to mass times acceleration. Nature has a very coincidental fact that the weight at the surface of the Earth is the mass times the gravitational acceleration. So keep that in mind, and that's what that second bullet is kind of implying for you. Okay. Actually, the third bullet is applying for you. It's part C. And remember, vectors in the same direction have to have the same sign. And you don't ever want to look at a vector in the x direction and combine it with a vector in the y direction. That doesn't work. Vector addition doesn't work that way. You have to look at components that are perpendicular to each other, often x and y. Remember, if you make a direction positive in the x direction, the opposite direction must be negative. Conventionally, we go right is positive, left is negative. Conventionally, we go up is positive in the y, down is negative, but those are just conventions. All right, so let's move on to the first problem here. And it looks complicated, okay? I've got 3 blocks, a hand putting a tension T3 on the first mass, and then there's a tension on the second mass, which we're going to call T2, but that tension is also acting on M3, okay? Then I've got a third cord with a third tension in it, which connects 2 to 1, and just looking at the given information, the masses are, for mass 1, the smaller one 5, for the middle one 10 kilograms, and the last one 15 kilograms. And we do know that the acceleration, unfortunately went over 2 lines, the acceleration, which must be this way, is equal to 5 meters per second squared. Okay, and so what we want to know is, what are the 3 tensions? What are T1 and T2 and T3? And the advice, and again, I stole this from Paul Mikulski, Dr. Paul Mikulski at the Naval Academy. He says, stay local. Okay, a lot of people try to make some composite figure which allows them to calculate all the tensions all at once. And the whole moral of this problem is to tell you, hey, work one object at a time. Work mass 1, work mass 2, then work mass 3. And you see, if you do it in the right order, it's not all that hard. And so I'll start out with some free body diagrams. And there's mass 1. And I better write that there so it's out of the way. And if you look at it, there is a normal force on mass 1. There is a weight force from mass 1. And that's why I'm subscripting, because there's going to be a normal force for mass 2 and a normal force for mass 3 and also weight forces. And then there is a force right there, which is called T1, which is acting on the first mass. Can anybody see another force that I ought to be including in the free body diagram for mass 1? I don't. Okay, so now let's go on and look at mass 2 here and do the same thing. There's a normal force 2. I'm making it a little bigger because, I mean, it's got a bigger weight, and so it probably has a bigger normal force. So I'm making those vectors a little longer, not worried about scale too much. Okay, I have T2 pulling this way, and I have T1 pulling that way. Okay, and you may go, well, why? You could make a third law argument about that tension. The tension that is pulling on mass 1 has to be equal and opposite to the tension pulling on mass 2. And so they are, right? Look, T1 is going to the left, T1 is going to the right. They're operating on two different objects. The means by which that tension is being applied is that rope or cord, and they're equal in magnitude. By Newton's third law, they must be, okay? And then so we're good to go here. We got one more mass to look at, mass 3. And let's see, it has an even bigger normal force because it has an even bigger weight, because this one's 15 kilograms. Okay, so there's weight 3. And of course, tension T3 is pulling that way. And again, another action-reaction pair, T2, pulling that direction. Notice T2 is acting on two different objects and pulling in two different directions, but with the same magnitude. Again, Newton's third law in effect here. And so what I hoped I drew is that on mass 2 here, the one in the middle, I think I made T2 just a little bit bigger than T1, and it has to be if I'm going to have an acceleration to the right. And T3 must be a little bit bigger than T2, again, if I'm going to have an acceleration to the right. Well, I guess it's time to do math here now. I'm just going to say this once because it's true for all three of the objects. In the y direction, what's the sum of the forces? And the question is, are any of these masses moving in the y direction? And the answer is no. So they are in equilibrium in the y direction. So for all three, the sum of the forces in the y direction must be 0. And so for all three, that means their normal force is equal to their weight. And I could subscript that with a 1, with a 2, with a 3, and we're done talking about, oops, go away, I don't want that. You're not seeing it. I had a little toolbar came up and covered all my work on me. It's gone now. So everybody good with that idea? However, in the x direction, in the horizontal direction, the sum of the forces in the x direction acting on mass 1 has to be equal to mass 1 times its acceleration. Well, we know its acceleration, it's given. It's 5 meters per second squared. And if I remember right, the mass of mass 1 is 5 kilograms. And in the x direction, I think I only see one vector, one force, the tension. And so that tension has to be equal to the mass, 5 kilograms, times 5 meters per second squared. And so tension 1, 25 newtons. It is that simple, okay? And as I said, a lot of people try to make this problem a little more complicated than it needs be by somehow combining things and not just working through the process. Draw the free body diagram. Once you see this and you look and you say there's only one force in the x direction, you go pretty easy. Now, that second mass is going to be a little harder, but you do the same thing. The sum of the forces in the x direction, and this is now mass 2, has to be equal to mass 2 times the acceleration. Notice 2 and 2, 1 and 1, right? All right, well, a little harder now to get the forces in the x direction because there's 2 of them this time. So the sum of the forces is T2 to the right, T1 to the left, And that has to be equal to, I can fill in some numbers here, I guess. Let's see, mass 2 we said was 10 kilograms. And of course, the acceleration, they're all moving together, is 5 meters per second squared. And I also know what T1 is, don't I? I can bring that right over there. And so doing a little bit of algebra, T2 here is equal to 25 newtons, bring it to the other side of the equation, plus 10 times 5, that's 50 newtons. And keep in mind, a kilogram times a meter per second squared is also a Newton. And so apparently my answer for the tension T2, 75 Newtons. All right, I'm running out of room here because I write too big like a gorilla here. But let's do the same thing now. I'll get the free body diagram in the screen here, so hopefully you can see it. And the sum of the forces on in the x direction on mass 3 is equal to mass 3 times the acceleration. And once again, the sum of the forces is T3 to the right. See it here? There's T3 minus T2 to the left. And that's got to be equal to mass 3 times the acceleration. I'm being a little inconsistent here, but that tells me that T3 is equal to T2, bringing it to the other side of the equation, 75 newtons, plus, I think we said this one was 15 kilograms, times 5 meters per second squared. That's a 5, okay? 5 times 15, 75. Let's see, 30, 60, and another 50. Yeah, 75 plus 70. Oh, I got that one then. So that must be 150 newtons, okay? And while the problem looked a little complicated when you first started, if you break it up into 3 pieces, stay local, as Dr. Markulski from the Naval Academy recommends we do, just work each one at a time, the problem really isn't that hard. And hopefully that makes sense. Any questions on that one? Excellent. All right, look, I'm even doing pretty good on time. I'll be able to give you some time to work on it. Here's the next problem I want to do. This one's a little bit complicated because it requires some components, some trigonometry, okay? And so I guess let's first of all just kind of identify the forces and read what it says. Let's see, the mass of that block is 15 kilograms. So we'll keep that one in our mind here. Let's see, the block is accelerating upwards with the acceleration 1.2 meters per second squared. The angles are 24 degrees right there on the incline. And then there's a tension in a cable. We don't know how big it is, but that thing is kind of pulling up, but is 12 degrees above the incline itself. So total of 36 degrees, 24 and 12, 36. But I don't think you're going to need the 36. We just have to see that angle right there. Okay, everybody kind of understand the given information and what we're trying to find? We're going to try to find the normal force. And in the last problem, remember the normal force was always equal to the weight because everything was nice and horizontal. And that's sometimes true. But one of the morals of this problem is it's not always true. It's not always true that the normal force is the weight. And in this case, it won't be. Okay, but what do we have to do? We have to identify forces. Since I brought it up, there must be a normal force. There must be a weight force. Okay, I got this tension force pulling this way. Okay, and I don't know what good coordinate system I want to work. I've only got 3 forces, but they are kind of, none of them's along a principal axis. But the acceleration and the normal force, if I make an axis tilted like this, okay, well then the normal is along the y direction, the acceleration is along the x direction. Of the 4 vectors I've got right here, the tension, the normal force, and the weight, and the acceleration, 2 of the 4 anyway are along this coordinate system, so it might not be a bad choice. And so that's what I'm going to draw here. And I always recommend a light coordinate system. Okay, and as I said, there's the x direction, there's the y direction, the acceleration is that way, so that's good. And the normal force is that way, so that's good. And the tension, unfortunately, is right about there, okay, where this is a 12-degree angle. Okay, and similarly, the weight would be down over here, okay, And this angle right here is the 24-degree angle. And so I'm going to write weight the way we often do now, since our reading for last night said weight is the mass times the acceleration due to gravity. We're good to go. And ultimately, right, we need to find the sum of the forces in the x direction and the sum of the forces in the y direction in order to determine well, in the y direction, I expect the sum of the forces are going to be 0. In the x direction, the sum of the forces are going to be the mass times the acceleration in the x direction. That's problematic, though, because we have to do some component work here. And I guess the first thing is I have to realize that the tension has an x component and the tension has a y component. Okay, and I've drawn them in those colors. And once I have those components, I don't need the tension anymore. Those two components replace the tension. And similarly, the weight, I'll draw it in a different color here. Go green today. The weight has a component in the x direction, weight x, and remember weight is just mg, and weight y. Okay, and so I think that has to be our first step. We got to get those components. You can't get the problem right unless you get those components. So let's work on that. I guess, and since I'm working in blue on the, we'll go back to blue. Let's see, the tension in the x direction, well, that's adjacent to that 12-degree angle. So that would be the unknown tension, okay, times, and now which trig function? Cosine or sine? Adjacent to the angle, cosine of 12 degrees, okay? All we can say, because we don't know the tension. The y component of tension is the tension, well, once I've decided cosine here, these guys go together, right? If you get one wrong, you're going to get them both wrong. And that's just the way life is, I suppose. It wouldn't make sense to make them both cosine. That's what we know. Got to do the same thing for the weight. The x component of weight is the weight itself, which is mg. And now here's the question. The angle is with respect to the y-axis, right? If you don't like that, it's right there. Okay, there's the 24-degree angle. Okay, so I guess if I'm looking for the x component, it's the opposite side. And so I must be using the sine of 12 degrees, dispelling the myth that some students have that x is always cosine, y is always sine. Only true if the angle is with respect to the x-axis. If the angle is with respect to the
Dr.
y-axis,
Tukolsky,
that's reversed. Yes, go ahead.
isn't the angle for weight?
Who is this? You're absolutely right. I see what you're saying. I wrote the wrong thing. I said it too. Who is this?
Katie.
Katie? I owe you another point, Katie.
Thanks.
Good catch. Yeah, you see what she's saying? I wrote the wrong angle here. Is that what you were about to say? It's a 24-degree angle. There we go. Thank you. Point to Katie. You got the last one too, right? I gave you 5 out of 4 on one of the worksheets. All right, and the y component is equal to m times g. If I've used sine for the x component, must be using cosine for the adjacent side to get the y component here. And I don't know why I didn't go to green. I just didn't shift my pen. All right, so now we're set up. We've got everything. Oh, we can actually get numbers here, can't we? Because we know the mass of the block. It was 15 kilograms. G is 9.8 meters per second squared. And the sine of 24, my calculator knows the answer to that. I don't know. It's somewhere around, that's 24. Somewhere around, oh, I don't know. Sine of 30 would be a half, so it's a little less than a half, right? In any event, I can put all those numbers in my calculator. Make sure your calculator's in radians. Big mistake. I get 59.8 newtons. All right. And again, on the other side, I know 15 kilograms times 9.8 meters per second squared, and I multiply by the cosine of 24 degrees. Kilogram times a meter per second squared is a Newton, and I put all this in my calculator, I get 134.3 newtons. Always a good thing to calculate out the numbers, I guess, if you know them, and you don't want to work
Dr. Tukolsky,
symbolically. Yes?
you might have explained this earlier, but you just said to make sure your calculator's in radians,
Yeah.
but we're doing it in degrees.
What did I say? Did I say radians?
Yeah.
Who's this? Because if I said radians, you need.
In radians.
Yeah, who are you? Who's talking? I'll you a point too if
It's
I said
Katie
that.
again.
Katie again? Oh man,
It's
Katie,
Katie.
you're killing me here today. You're taking points away from me. Oh well, yeah. If I said radians, it's because I had a senior moment there, and you're the numbers are in degrees. Make sure your calculator is not in radians. Okay, and if you don't know how to switch with your calculator, that's something that maybe the skills session. Max Tucker and Anna, they're pretty good with multiple types of calculators they've been using. But you have to know that. You might have to go to your user's manual, make sure you're in degrees if the problem is in degrees. All right, great. Sorry if I said the wrong thing. It's hell grown old. All right, so anyway, now we're ready to solve the problem. Anybody have a preference which direction they want to work first? I'm going to go the sum of the forces in the x direction first. I don't know. And if I look at my free body diagram, in the x direction, I guess I have a tension in the x direction, and I have the x component of weight, right? Anybody see any others? Nope, that's all I got. Okay, so those are the two we have to add up. The sum of the forces in the x direction are the weight, which is to the left, and the tension, which is to the right. So let's make it the normal order. The tension in the x direction minus the weight in the x direction. And those two forces have to be equal to the mass times the acceleration. Okay, and so we don't know what the tension in the x direction is. We do know what the weight in the x direction is. We just solve for it. So the tension in the x direction must be equal to the weight x component plus the mass times the acceleration. And this is style where you decide to start putting in numbers. I'm going to do it right here. No right answer as to when you put in the numbers, but at some point now we have to. 15 kilograms. And what was the acceleration? I have to go back and look at my given information. 1.2. Yeah, there it is. I put a red line under it. Okay. 1.2 meters per second squared. Okay. Put those in my calculator, add them up, and I get that the tension in the x direction is 77.8 newtons. But that isn't what the problem asks for. The problem asks for what the tension is. What's T itself? We just found the thing that's circled here. We found the tension in the x direction, but that's okay. I've got an equation right here that relates what I'm actually looking for, don't I? So all I have to do is take that equation and manipulate it. The tension itself is equal to the tension in the x direction, the x component of the tension, divided by the cosine of 12 degrees. Okay, put 77.8 newtons in there and divide by the cosine of 12 degrees, and I get just a little bit bigger, 79.5 newtons. That is the overall tension in the cord that causes the 1.2 meter per second squared acceleration. All right, problem also asks for the normal force. The normal force is often associated with the y component of acceleration, Newton's second law, but there is no acceleration in the y direction. So the sum of the forces in the y direction, let's see, let's look at the free body diagram. That's why we bothered to draw it. I've got the normal force acting up. Is that labeled at all? I drew it. Is that supposed to, that's the thing right here is supposed to be an N, I guess. I don't know what letter that is, but it should be a normal force, right? I have the y component of tension upwards, and then downwards I have the y component of weight, and that was the y direction, okay? And I have no idea what I was writing right there. But the sum of the forces in the y direction, normal force upwards, the y component of tension upwards, the y component of weight downwards, and it's not moving in this direction. So that sum has to be equal to 0. And so I guess the normal force here must be equal to the y component of weight minus the tension's y component. Okay, well, let's see. What is the y component of weight? Well, the good news is, I guess we took a moment early on in the problem to solve for it. 134.3 newtons. So I can use that. 134.13 newtons. And then I have to subtract off the y component of tension. And all we have for the y component of tension done previously is this. So we can work with that, I think. The y component of tension would be the tension, 79.5 newtons. Bring that right there. And then if you remember right, what I was just looking at was the sine of 12 degrees. All numbers I can put in my calculator. And when I do that, I get 117.8 newtons. And so I'm looking at these numbers now, and the last step, and I'm not overly rigorous on this, but it looks like I've got 2 digits for all the numbers here to use, and I should be attentive to that. I'm writing answers to 3 digits, and so I think I should probably make this just about 80 newtons is a good answer. And this is, oh, I don't know, you can go to 120 newtons, I suppose, if you round it to 2 digits. And so those are probably the best answers for this problem. Any questions on any of that? All right, well, once again, and these aren't due until next week. I go too long. This is a pretty straightforward problem. I did one very similar to it on the video last night, only in that
Dr.
case.
Tukolsky,
Yep, go ahead.
I think you put TY as the answer and not like
Did I make another mistake?
subtract.
Where are we?
So you found TY, but you
Right.
didn't subtract it from 134.3.
Yeah, if you take the sine of 12, it's a pretty small number. So 79 times the sine of 12. I did subtract this off. I'm not sure. This number right here, did I do that in my calculator? No, I didn't. But this is going to be somewhere around, I don't know, 20, roughly. Okay, so I took 134, I subtracted that.
Oh, okay, so you didn't write it out.
I didn't write it out. Yeah, and truthfully, it's not bad practice to write out what that is. I didn't, because I have a calculator where I can put that entire line in, and it'll tell me the answer is 117.8. If you don't, well, then it might be a good plan, good strategy to figure out what that number is. Okay, good to go on that now?
I have a question.
Thank you.
Go ahead.
So is the applied force the tension? Like what?
Yeah, let's read what the problem actually asks for. Yeah, the applied force is the tension. Yeah, in fact,
Okay.
yeah, absolutely. Yeah, so if you read the problem, it says an applied tension force. So right here, this line equates those 2 words for you. All right.
Okay, thank you.
You bet. Yeah. And that's truthfully, if that's ever a question on an exam, by all means ask that one. Okay. Yeah. The nomenclature of applied versus the tension, but the only force that a human being might be, generally we think of human beings or machines or something apply forces to objects. And in this case, the applied force is a tension. All the rest just exist because of contact with a surface or because of the fact that the earth is exerting a gravitational force. The one that isn't because of a surface in contact or the earth is that applied tension. Okay, other questions? All right, well, for Monday then, 2 other problems. One's an elevator problem similar to the one I did in the video last night, okay? And so my recommendation always is a free body diagram, right? Read the words carefully and decide what direction the acceleration is in. The elevator is moving upwards and slowing down. So similar to our Mars landing polling question, right? And then do the free body diagram, sum the forces in the y direction, and set them equal to that mass times acceleration. Pay attention to your signs. Vectors in the same direction must have the same sign. Vectors in opposite direction must have the same sign. And then here's just a problem. You're going to have to bring in some kinematics. So this might be a good review problem for the exam, okay? You see that the person is going at 4.5 meters per second and then hits a rough patch of snow and comes to rest. And so final velocity is 0. And I guess you have to figure out, you know what the friction force is, you have to figure out what the acceleration is, and then figure out how long delta x this person is traveling before it comes to rest. And so I think one of the review equation here is that the final velocity squared is equal to the initial velocity squared plus twice the acceleration times the displacement. Well, you know what that and that is, because starts at 45 or 4.5, ends at 0. The acceleration, I think, comes from the friction force when you do a free body diagram, and then the only thing you're left to solve is delta x. And so that's how you do that problem. I see I'm 1 minute over on my time here, so I got to let you go. We'll see some of you who have questions on Friday morning. If you're good to go on the exam, get it done by midnight, 1 minute before midnight. Okay, get it loaded, everything uploaded 1 minute before midnight. We'll see the rest of you, I guess, on Monday morning then. And good luck on the exam. And I hope everybody gets A's. That's what we want. That's the goal here. All right, questions? I'll stop sharing. And then everybody have a great day. And we'll see you either Friday or Monday.
Thank you.
And I'll be hanging around. I'm going to stop the recording. Anybody have